Thanks for being here. I'm really excited to present Dr. Dan Horton from Northwestern University as our seminar speaker today. I'll do my best to speak to all his achievements, but I really encourage you to go to his website and read his bio. It's quite entertaining and has a lot more information in there. Yeah. So Dan did his bachelor's in physics at Tulane University, and he also took a very heavy geology class load on the side just for fun. And then after that, he entered the Air Force. And as part of his Air Force training, he earned an atmospheric science degree from Texas A&M and spent some time in Germany and Italy as, I think, an aviation meteorologist. Is that accurate? Okay. So that's pretty cool. And then after he left the Air Force, he went on to pursue his PhD at University of Michigan in paleoclimate, which blended his love of geology and meteorology and getting to spend time in the field while also learning about numerical climate modeling. And then after that, Dan went to do a postdoc at Stanford University. And there, his work focused on the more modern climate, looking at impacts of human-caused climate change on air quality, disease, and extreme weather events. And that's where I met Dan while I was doing my PhD in the same research group. And on a personal note, Dan was a really awesome mentor, unofficial mentor, and office mate. And so it really didn't surprise us when he got a faculty offer from Northwestern University. And so right now, his climate change research group studies a variety of climate change related topics, including extreme climate events, surface hazards, air quality, and public health. And he recently received an NSF Career Award to study the air quality, public health, and equity implications of transportation electrification. Doing a lot of cool things. So please join me in welcoming Dan today.
Thanks very much for having me, and thank you, Danielle, for the invitation. It's good to be back in Texas. When I left Texas many years ago, I tried to never come back, but I was invited, so here I am. If you've ever been to College Station, you'll know why I spent so much time in Austin when I was in Texas, so it's good to be back in Austin too, although it looks nothing like it looked 20 years ago, as many of you probably know. Yeah, so today I'm going to talk about adapting WRF-Hydro for use in land surface hazard applications. But before I get there, I call myself an Earth system scientist, a climate scientist. And this is a slide I like to show to academics so they can disagree with me, or to the public when I do public outreach. And it's kind of my conceptualization of where the field's at, or at least where my head is at in terms of things that I find interesting to research. And on the x-axis, you can see a cartoon diagram of time, and then our understanding advances on the y-axis. And what you see is that, physics and chemistry, we know a lot about the physics and chemistry of the climate system, the atmospheric system, so much so that we can write really fancy numerical models and simulate them pretty well with high fidelity. We can use these models to assess the intersection of climate change in the atmosphere with people, places, and things, and get at the impacts of atmospheric processes and climate change. And at this stage, I think we're to the point where we can start to explore solutions. And that's the piece that really invigorates me and invigorates my research, and has led to kind of the transition that I've made when I became a faculty member to basically do whatever I want, as long as I could get funding for it, right? Which is the beauty of academia. Which allows me to do lots of different things, particularly because I'm at a place like Northwestern that has no other atmospheric scientists. And so I don't step on anybody's toes. I can do what I want. It's pretty nice. All right, so before I talk about what I'm actually going to talk about, I thought I'd mention a couple things that I also do in case we have a talk later, or you want to have a talk later. By far, the vast majority of what I'm funded to do and what my research group has been doing lately is estimating tract level air quality in Chicago. And then we extend that to look at public health impacts and equity implications, particularly of vehicle electrification. We do this using a model called WRF-CMAC, which is an EPA regulatory grade model. And we do this at a very high resolution. So it's down at about 1.3 kilometers. which allows us to say things about impacts on populations, particularly populations at the census tract level, which is handy because we can look at demographics and say things about income level or race and disparities and exposure, things like that. So if you want to talk to me about that, I'd be happy to. I also am helping the city of Chicago. I lead a team of an incredibly disciplinary team that's building a heat vulnerability index for the city. This is a project that I'm doing with the Department of Public Health, the Department of Environment in the city, but also with community members. So this is a community-based participatory research project where community members are helping us make decisions. And in fact, in terms of the hierarchy, they're on the same level as the academics when we make our decisions about the sort of data that goes into this tool. This is a tool that will ultimately be used for policy. In the Climate Action Plan in 2022, it was stated that Chicago is going to develop one of these. Well, my team is the one that's developing this, and we'll use this tool to make policy decisions, allocate resources to different neighborhoods. So where are we going to put a cooling center, that kind of thing. So really cool application kind of science that we're working on. But today I'm here to talk to you about an NSF Prevents funded project. May have been the very last NSF Prevents funded project. We're now in, I think, our second year of a no-cost extension, so we're probably close to the last one that's still out there. But this particular project was called Defining Precursors of Ground Failure, a multi-scale framework for early landslide prediction through geomechanics and remote sensing. The team was led by this gentleman over here. This is Giuseppe Buscanera. He's a geomechanics professor in the Department of Civil and Environmental Engineering at Northwestern. It's very interdisciplinary. Karen Daniels is at NC State, and she is a physicist. And she spends most of her time thinking about piles of sand and using light up LED panels and crushing them together and doing really cool physics type things. The team also includes Al Handberger, who's at JPL. He's an actual geologist or geomorphologist. He also does a lot of work with remote sensing. And then the person that's the engine of my work on this is my former graduate student, Chushuan Li, who's now a postdoc at UCLA. And so this project is focused on landslides, and specifically landslides in the vicinity of Highway 1 in California. Just looking at that picture, you can probably tell two things. It's ridiculously beautiful, and no wonder there's landslides there, right? It's a perfect place for landslides to occur. They built a road on the side of a cliff, essentially. It runs all the way north-south up and down California, and if you've never had the opportunity to go, you can always read a book about it. There's great ones. Jack Kerouac wrote one, but you can also just go and have a great time. Although, as I'll tell you, there's some challenges to driving up and down Highway 1 right now. All right, so here's some of those challenges. This is just the latest report of incidents along Highway 1. These numbers 1 through 4 here are just places where maybe it's impassable or you're down to one lane. And these all have to do with land surface hazards and how they interact with people in their lives. Believe it or not, there are people that live out here. It's not just a tourist destination. But Highway 1 is a huge economic engine, right? You might be wondering, like, why do we support this road if it's such a hazardous place? Well, it produces billions of dollars every year for the California tourist economy. And so Californians want to keep it around. But there's challenges to that. And so this is the Mud Creek slide. This occurred in May 27th of 2017. The Mud Creek slide, it was the reason we got funded from NSF. It was a slow-moving landslide, which meant that it was creeping along nice and slow year after year. It might accelerate when the precipitation increased in the rainy season in California, but then it would slow back down during dry periods. And it was doing this for year over year over year until May 27th, when an atmospheric river came in and dumped a tremendous amount of precipitation on the top of it, and this failure happened. This failure cost about $50 million to replace. They've since rebuilt it. They've put in some really fancy engineering things. If you're ever out that way, you can stop and hike up and see them all. It's a really beautiful place to be, but it also makes you think about standing just below it and all the material that might fall on top of you. Another failure of the highway is more germane to what I'm going to talk about today, and this is the Rat Creek debris flow that occurred in January 28th of 2021. In this case, it's a much smaller feature, but in the case of driving down a road, it doesn't really matter whether it's big or small. You can't get past this, right? This is a wildfire debris flow, which means that upstream of here, we had a lot of a large wildfire of varying severities in different places. Another atmospheric river came, drove a bunch of material down the road and washed it out and made tourism in this part of Big Sur impossible. All right, so landslides don't happen only in places like California along Highway 1, they happen worldwide. And from 98 to 2017, landslides have affected about 5 million people and claimed over 18,000 lives. And so our ability to understand these events and potentially predict these events is something that could be quite valuable. And so let's get on the same page first, some definitions about landslides from the USGS. The USGS says a landslide is the movement of a mass of rock, debris, or earth, lowercase earth, moving down a slope. Landslides are a type of mass wasting, which denotes any downslope movement of soil and rock under the direct influence of gravity. There's 4 modes of slope failure. We have falls, topples, slides, spreads, and flows. And we further subdivide these categories by geologic material, so rocks, debris, earth. And so this bottom picture, whoops, wrong one. This bottom picture here would be classified a rock fall because it's rocks falling. Whereas on the right over here, we have a picture of a debris flow, right, inundating this town. The triggers that cause these sorts of events are various. So we have co-seismic events, so earthquakes happen, and then we have slope failures shortly thereafter. It can happen from glacial retreat and ice thawing, from rapid snowmelt. Human activities can destabilize slopes, and then we can have precipitation. And today I'm mostly going to talk about precipitation events. These type of events are super common in California. There's the Mud Creek event I mentioned above. And then there is the debris flow, wildfire debris flow event that happened at Rat Creek. And just this past year in January and March of 2023, there was over about 1,000 landslides that occurred due to the landfalling of about 9 atmospheric rivers, one after another in California. It was one of the wettest periods in San Francisco history. And then in February of just this year, another 592 landslide occurred in a week. And these numbers are underestimates, right? Often we only report landslides that co-occur with roadways that we're driving down. There's often many landslides out further afield that don't get reported. And many of these landslides in California are driven by atmospheric rivers. It's what we call the dominant synoptic weather system that produce landslides in California. These are long filaments of moisture. They come in relatively low on the ocean, pushed along by low-level jets. And when they intersect the land surface, particularly a land surface that has some topographic relief, they get squeezed out like a sponge, and they drop a whole bunch of moisture on the land surface in the form of precipitation or snow if you're higher up in the Sierra. And so they're relatively not wide, right? From tens to hundreds of kilometers across, but they're very long. And so these are giant scale features that are interacting with the continents. And so from thinking about a land surface hazard perspective, we need to start thinking about regional scale tools to resolve the impacts of these events, right? If they're affecting thousands of kilometers at a time, then working from a catchment scale to catchment scale isn't necessarily going to get it done for operational warnings for these sorts of events. The other piece to mention is that ARs are incredibly important to the delivery of water to California. So about 30 to 50% of all the water that falls in California comes from atmospheric rivers. And when we're talking about lots of water, so extreme events, about 80% is associated with atmospheric rivers. So from a precipitation triggering standpoint, there's two mechanisms that I'll present or talk about. The first is infiltration influenced landslides. So this is when we have rainfall falling on the surface, it infiltrates into the land surface, the groundwater table rises, the shear strength decreases, and a slope can fail. Slightly different physics is these runoff generated landslides. In this case, rainfall falls along the surface, overland flow or runoff occurs again, we get entrainment, erosion, and ultimately debris flows. And these are often channelized features. So they happen in what previously were stream beds. These are incredibly important in wildfire burned areas. And both of these call out the fact that we really need to think about hydrology for predicting these rainfall triggered landslides. And so operational products that are out there right now that are being used to create warnings for different communities are largely data driven. They're not numerical modeling based, or at least they're not physics-based numerical modeling based. They're data driven. And so in this case, what you're looking at here is a plot from Staley et al. That looks at intensity duration, right? And so you're seeing these curves, which are the thresholds, upper level threshold and the low level threshold. I've never worked with a mouse that I point at a tiny screen, so forgive me. And along the x-axis, you're looking at the duration of precipitation, and on the y-axis, you're looking at the intensity of that precipitation. And they develop relationships about where that threshold is in terms of duration and intensity. And then they verify it by looking at where debris flows occur and don't occur. And so they've established these relationships using lots of observational data. This is a fast and economical way to do this. You can just look at the weather forecast and say, okay, the weather forecast says this, so I'm going to put a warning out that says, yes, debris flows are likely or they're not likely, right? The trick is they're regionally sensitive, right? So these have to be done everywhere that you might have a situation like this. And there's lots of uncertainties, and you also have to start thinking about the fact that precipitation patterns are changing. And so non-stationarity is a factor here. But with these tools, the USGS operationalizes them and creates emergency assessments of things like post-fire debris flow hazards. And so in this case, they take the ID thresholds on the left and they create a design storm. And so in the case of the USGS, they take a 15-minute intensity and they apply that amount of precipitation uniformly across their burn scar, right? So in the USGS model, precipitation doesn't vary over space, which as an atmospheric scientist rubs me the wrong way. But that's what's done. It's state of the art. It's where the warnings are coming from. They also consider the severity of the burn across the different catchments. They also think about the material that might be movable within those catchments. And using likelihood models and regression-based volume models, they come up with these hazard maps. And so if you're in the dark red area, you have a high likelihood, if you're having an intense precipitation event, to experience debris flows. They make these once a year. And so if you go to the website and you happen to live in a place that had a wildfire burn scar, it says something on there like, if you want us to make you one of these, let us know, kind of thing. So it's not a huge operation, right? They don't do this for every single burn scar that exists. There has to be some reason behind it. And as far as I know, it's just a few people working on this. And so I think number one lesson from this is USGS needs more resources. All right, so that's kind of the state of the art and how these post-wildfire fire debris flow hazard maps are created and put out from an operational perspective. I see stuff like that, and I think we can do better, potentially. And so I am not a hydrologist, but I had a person on my NSF proposal team with me, Jiali Wang, who works at Argonne National Lab, and she had done some work using the WRF-Hydro model in the past. And so this is a physics and process-based model that simulates the entire hydrological cycle, and I'll get into a little bit more about what it does and how it does it. But essentially, it couples both atmospheric and land surface processes, and it resolves a lot of the key hydrometeorological processes that are relevant to landslides. And maybe most important is that it's a physics-based model, which means that it's adaptable to different climates, potentially, or different climate conditions, which is something that's quite important to us moving forward. All right. Now, most current landslide investigations that use hydrological models focus on individual catchments. There's not a lot of people that think about this from the perspective of the scale of the meteorology. And so often these hydrological models are applied at single catchment scales at really high spatial and temporal resolution. And they attempt to capture all the processes, all the physics that are involved. So the timing of the flooding and the flows, and also the entrainment of sediment, and where that then is deposited after it's been entrained within the flow. But the key thing that I thought was missing from all of this was that there was no regional scale hydrological models involved in attempting to do this. And so that's where we came in. We decided to try to adapt WRF-Hydro for landslide research and susceptibility prediction. And so it's a regional scale physics and process-based model. And this is how we do it. So first off, we need some meteorological forcing data. And so that is things like precipitation, but it's also other meteorological variables that are important. We input those into the NOAA MP, which is a land surface model. This model constrains things like moisture fluxes, energy fluxes, so on and so forth. But it also looks at soil moisture. And so it's got 4 different soil layers within it. And the water that is in excess, so excess water from this model, then gets sent via 2-way coupling to a terrain routing module in WRF-Hydro. And this terrain routing module considers both subsurface flow and overland flow, which are both important to landslide prediction. If some of that subsurface flow or overland flow intersects with some of the channels within this model, it gets sent to a stream flow routing model. So this is the channelized stream flow that will give you stream flow discharge. And then there's also a groundwater bucket model that if you have a surplus of moisture, you can overflow this, but at all times, if you have some groundwater, it will seep in to the channels over time. And so this is kind of the conceptualization of the model. Both the terrain routing module and the streamflow routing module are wave diffusion equation solvers. In the case of the channelized streamflow, it's in 1 dimension. In the case of the terrain routing, it's in 2 dimensions. This model is used extensively by hydrologists. And in fact, it is the core hydrological model of NOAA's national water model. And so at any one time, you can go on this website and see how all of the rivers, all the major rivers across the continental United States are being predicted in terms of their discharge, their potential for flooding, so on and so forth. Okay, so what do we do with this model? Well, to adapt it to landslide research and susceptibility, we do a number of different things, and I'll go through these one by one. But the first thing we do is try to improve the model to simulate landslide relevant hydrological variables. So this is a study that we ended up publishing in Water Resources Research last year. And we were really focused on whether the model could accurately simulate antecedent soil moisture. Antecedent soil moisture is super important from a landslide perspective because it helps determine inundation. If you're already wet, it's hard to get water in a saturated soil, right? So that seems like something we should be able to resolve. We are also interested in the question of, if we get soil moisture better, do we then automatically get stream flow better, right? Compared to the observations that we have. And so what we did here is swap out some of the parameters in the model to do our calibration and validation. And so very quickly, just kind of going through the WRF-Hydro setup again, but with a little bit more information. To provide meteorological forcing for this model, we used a reanalysis product called NLDAS. And then the precipitation we didn't take from reanalysis, we took from a different data set called MRMS. MRMS is multi-radar, multi-sensor precipitation. It is 1 kilometer resolved, and it is hourly, and it is CONUS. So it's a very high resolution product, spatio-temporally, and we use that as our precipitation forcing in this model. It is built both from weather radar data, but also gauge-informed data. So the gauges inform the weather radar, and that's why we have this spatial coverage. It's an interesting product, and it has proved quite valuable to us, and we've seen a number of other people start to adopt it in the land surface hazard community, among others. It's not a thing that I created, it's created by others. All right, in terms of spatial resolution of other things, WRF-Hydro and its various components are resolved at 100 meters. NOAA MP is resolved at 1 kilometer. And then the individual streams that we're simulating here are based on the stream order of those streams, and they range from anywhere from 1.5 meters all the way up to 100 meters. And what we get output is 100-meter soil moisture information and stream flow. And so we applied this to our study area, which is in the Coast Ranges of California, where Highway 1 exists. What you'll see on this map is that this is elevation, so topography is listed here. The blue, or rather the purple crosses, are where we have USGS stream gauges. The circles and triangles are where we have soil moisture observations. So we don't have a ton, but we use what we have to try to verify what the model is showing us. And so one thing to mention is that it's a complicated area, right? It's got a tremendous distribution of topographic slopes. It's got a tremendous distribution of vegetation, so on and so forth. So it's a challenging place to do work. And what would typically be done using WRF-Hydro or another hydrological model is to calibrate the model. We calibrate the model in different ways, but the standard way to calibrate WRF-Hydro is often an iterative calibration, where you run the model and then you slightly tweak the parameters and run it again, and so on and so forth. And it's incredibly expensive. And so instead, we tried something different in this case. And it turned out to be incredibly simple, but quite valuable to us. What we did is, instead of relying on the default soil parameters that are in WRF-Hydro, which are sourced from a paper from 1984 called Cosby et al., that looks at a whole bunch of different soil parameters. I'm just going to show you porosity here, and breaks these up by 16 different soil types and resolves this information at 1 kilometer. We used a new data set by the name of Polaris. Polaris is from the soil survey, and I don't have my notes here, so I don't know the exact name, but it's the soil survey of the US. I don't know the exact name, my apologies. But basically they acquired accumulated data from the past 100 years from observational analysis. So people went out and dug soil pits in various locations. All this data gets accumulated. There's some gaps in that data, and it gets filled in with a number of different sources. And so the Polaris piece of this is taking that observation-based data set, SERGO, and filling it in using machine learning algorithms. In this case, it's a random forest. And what it produces is a finer resolution data set. It's resolved at 30 meters across CONUS. It's got much more detailed information, and it includes uncertainties. And so the Polaris data set is probabilistic. And so we can look at all pieces of the distribution in terms of a grid cell and its soil properties from the 0 to the 100th percentile, right? So we can run this using the 5th percentile numbers or the median numbers, so on and so forth. So it gives us a lot of interesting data to work with. And what we do is replace all of this information in WRF-Hydro with this newer data set. And so we run a couple different sensitivity simulations. The first is we're using this Polaris data, and we initially identified the most sensitive variables from a soil perspective and replaced them with this newer data set information. And they turned out to be porosity, saturated hydrologic conductivity, and clay fraction. And so we used median values from the Polaris dataset to replace what was in WRF-Hydro. And so that becomes one sensitivity simulation that we ran that we'll call Polaris 2-meter soil. And then we ran a second simulation that we'll call Polaris 40-centimeter soil. The difference between these two simulations is that the default soil thickness in WRF-Hydro is 2 meters, and it's 2 meters everywhere. Probably one of the biggest weaknesses, in my opinion, of WRF-Hydro, but it's the way the model is. In the case of the 40-centimeter soil, we looked at that Sergo data set and looked at the average soil depth in our domain, and it turned out to be 40 centimeters, and so that's what we used for that sensitivity experiment. All right, so what does this look like? So this is a plot of soil moisture, both observed and model simulated. So looking at baseline versus, in this case, Polaris 2-meter in red. This is from Gilroy, which is, if you've ever driven up and down the Highway 101 in California, Gilroy is the self-proclaimed capital of garlic. They have an annual garlic festival that I just learned while doing research for this talk. This is the kind of research I did for this talk. They got rid of their garlic festival during COVID, and they have not brought it back, which many people are very sad about. So I don't know if they can still claim to be the garlic capital of the US. Anyway, there is a soil moisture monitor, probably for growing garlic in Gilroy. And so this is just an example of one of the places that we did the comparison between what our model did and what we produced. And first we looked at correlation. And so our baseline simulation got a correlation of 0.86, Polaris 2-meter, bumped that up to 0.94. And so this is a 9% increase. Our root mean squared error decreased, and our Kling-Gupta efficiency, which is a combination measurement or metric that looks at mean, standard deviation, and one other thing that I can't remember, but if it gets close to 1, it's better. And so in this case, we improved that by 17% just by updating soil properties in the model. And so this is incredibly computationally efficient compared to the other way of attempting to calibrate one of these models. That second question that I mentioned about if we only update soil parameters in the model, do we also get some bang for our buck in terms of stream flow? And this is, again, is just one example, but in this case, we're looking, and we see that, again, our correlation increases, our squared error decreases, and in this case, the KGE increases by up to 290%. And so this is a huge benefit, both from soil, attempting to simulate soil moisture, but also get the discharge rate in the streams. And so this is a non-iterative method and uses open access soil databases to improve these landslide relevant hydrological variables. Probably the simplest study I've ever done, but it was incredibly powerful, right? Saved us a whole bunch of time. So kind of a big lesson in there, but also a cool result. All right, Now let's get to the landsliding piece of this. So we also, way back at the beginning, I said that we were funded to study these slow-moving landslides that transition to catastrophic failures, like the Mud Creek landslide. And we started down that road and realized that this model is not very good at doing that. And it doesn't do a good job. And because there's a lot of really interesting plumbing under the ground that really matters that this model is not capable of simulating. But one of our collaborators, Al Handberger, said, hey, have you ever thought about using this model setup to look at post-wildfire debris flows? And I said, no, I had not, but we can try it. Let's give it a shot. And so that's what we did. So in this case, we're looking at wildfire and its impact on surface hydrology, and how that might change overland flow and stream flow discharge. And we're going to do it in WRF-Hydro. All right, so wildfires modify soil properties and land cover characteristics to increase flooding and debris flow susceptibility. And so in a pre-fire situation, we have leaf litter and duff sitting on the surface of the land. We have entry of surface waters down into the soil column and into the groundwater. And then a fire comes through, and suddenly we have ash sitting on the surface. We no longer have the canopy of the trees that's able to intercept precipitation as it's falling to the ground, which turns out to actually be kind of important when it comes to motivating sediments to move. In some areas, particularly arid areas, we end up seeing waxes from these from the burned material, creating a soil sealing layer across the top of it, which means that when water falls on it, it no longer can penetrate and it rides across the surface. And that's super bad when we're talking about the rapid flow of extreme precipitation into an area. And so in California, we have kind of a perfect recipe for creating these sorts of events. California has lots of topography. It turns out you need gravity to have these kind of debris flows, and so you need some topography, you need some gravity. California also has frequent wildfires, and so these are areas that have burned in California from 1800s to present. If it burned before, it can burn again, right? And so almost all of California has at one point been on fire, which makes you want to move there, I'm sure. And the last thing to mention is that lots of atmospheric rivers, so lots of extreme precipitation events occurring in California. So the potential for post-wildfire debris flows is very high in California. The other thing to mention is that precipitation patterns are changing, right? Increases in intensity are happening. And so these are all things, good reasons to investigate these questions. Probably the most famous post-wildfire debris flow was the Montecito event. Montecito is very close to Santa Barbara, so you probably heard about this because Oprah talked about it, and this is where she lives. 26 people died from this event. I have a number in my notes on this slide that tells me how much it costs, but it was in the millions, hundreds of millions of dollars. So it was a very catastrophic event. It made a lot of news because it happened where people live, and it happened where a lot of wealthy people live, right? Which is another reason it made the news. Lots of structural damage, not a good thing. We don't simulate, or we haven't yet simulated the Montecito event, although it's been really well studied by USGS and many others. But in this case, we're gonna study that Dolan fire, and this is the event that triggered the collapse of High 1 at Rat Creek. And there were multiple other debris flows associated with this event. So the Dolan burn scar happened, I believe, in 2020, in the summer of 2020. And then in January of 2021, an atmospheric river came to town and dumped upwards of 300 millimeters of precipitation over the coast ranges. So the Dolan burn scar here is outlined in black. There's other burn scars that you can see up here, the Cruz, the CZU lightning, and the Carmel. And so this is another reason why doing this from a regional perspective is important. We know that if an atmospheric river is coming in here, it's not only going to affect Dolan, right? It's also going to affect much more of California. This project was done in conjunction with Noah Finnegan, who's at UC Santa Cruz. Noah was responsible for these yellow triangles. So basically the event happened and he drove south. And he's like, that one is by the road, and that one's by the road, and that one's by the road. And so all the observations we had for this event was from Noah driving around. And so at least we had something to compare our model data against. So I mentioned, I showed you the picture of Rat Creek, which is intersected with the highway. But there was also a number of others, like I mentioned, and this is a picture from Big Creek. This is a giant log jam that's up the channel. I'm a modeler, so I don't get to do field work very often. So when I do field work, I have to show pictures from it. This is one of the coolest things I've ever seen. I have been in the woods many times, just not doing field work, and I have never seen something like this. It was basically a redwood forest and this giant log jam in the middle of a channel. There is a human there. I don't know if you can see him for scale. I don't know how tall that human is, but the log jam is multiple humans tall. It's a really cool feature that was up in the woods. It's still there if you ever want to go there. At the bottom of this channel, there is actually a UC Santa Cruz research facility that has like a non-marked gate to get into it, and you're right there in beautiful Big Sur, and it costs like $17 a night, and researchers can go there. So talk to your colleagues at UC Santa Cruz if you need a research trip. All right, so what do we do in the model to simulate this? We're going to change parameters to replicate burn scar effects. And so we talked about this kind of cartoon diagram of post-fire conditions. The first thing is vegetation effects. So we set out a land cover in the burn scar to barren and sparsely vegetated. There's probably a better way to do this looking back at it now, because there are varying burn severities and burn scars, but we just blasted it all away for this simulation. So we reduce the canopy height, and that also reduces surface roughness. And so here's canopy height over here on the left. There's our Dolan burn scar, and you can see that we're way down at the end of the scale. Similar to surface roughness, which impacts our overland flow and the rapidity with which something might be able to get to a channel. So if all that rain can get to a channel real quick, we're going to have a bigger discharge and a more catastrophic event. The soil sealing effects. So to simulate this in our model, we reduce saturated hydrologic conductivity in this particular part of the world, so we weren't getting infiltration. All right, and here's what happens. This is hydrographs we compare to a USGS gauge. The USGS gauge is not in a Dolan burn scar. We had to work with what we had. We found one that was nearby that could have been affected by wildfire burn scars outside of our domain, or rather within our domain, but outside of the burn scar. And so here's what that looks like. We have our pre-fire scenario, that is the dotted line or the dashed line in purple. The USGS streamflow observation is the dot dash, the Morse code line here. And so you'll notice that the purple line looks nothing like the Morse code line, the dot dash line, right? So the default model does not at all capture what we're seeing at USGS. When we implement our post-fire characteristics, this is the red line, we suddenly see the hydrographs start to look very similar, right? And so what this is showing is that both the magnitude of this discharge and the timing of the discharge are affected by these characteristics. And you do see, the precipitation is up here on the top of y-axis, and you do see two pulses of that atmospheric river. In the default model, those pulses occur, and then they infiltrate into the soil and slowly make their way out of the system. But because of wildfire and all the processes that occur, it's way more instantaneous in our post-fire simulation. And so that was a really cool result. And what we were able to do is simulate peak discharge over the whole domain. And so the whole domain that we're simulating is on this plot. So you can look at that where the colors are closer to brown means higher discharge. We also, at the time, WRF-Hydro did not output overland flow. It calculated it, but it didn't give it to us. And so we ended up modifying WRF-Hydro so that we could look at the overland flow to see what effects that would have. And so we looked at all of these conditions, both peak discharge and overland flow at all of our different identified locations, and noticed that we had elevated conditions or elevated water in those places. Starting to get at that question of susceptibility and what wildfire does to increase susceptibility, we can look at catchment by catchment in terms of the normalized peak discharge. And so on the left-hand side here, maybe, I think I lost my pointer. On the base, oh, there it is. Nope, okay. On the left-hand side, the baseline simulation, this is improper timing, not as much magnitude. The burn scar simulation in the middle, you can start to see the reds pop out. And then if we do a difference between those two plots, you'll absolutely see the influence of the burn scar on the amount of peak discharge in these catchments. And if we walk through this, you can see that the yellow circles are the places that Noah Fettigan saw. Most of these places have elevated discharge or peak discharge, but then there's a few places that we don't have any information, but have high susceptibility according to our model. And what we did was use the Sentinel NDVI data to look at vegetation, changes in vegetation during this time period to try to confirm whether we might have seen some erosion during these events. And so in this case, on the left-hand side, the yellow catchments are the ones that have vegetation loss signals. It's just vibrated. I don't know if that means anything. And so on the right-hand side, you can see that these line up with rivers that we know about. So this is the Arroyo Seco up here to the north of our domain. And so this is an impact that's happening outside of the burn scar domain, but influenced by the precipitation that falls over the burn scar. The Nacimiento River is another location where we see vegetation loss. And lastly, the San Antonio River also saw impacts. So the key takeaways here were that this is an open source community hydrological model that typically is used to predict river flow. And we've applied it in kind of a fun way to predict regional post-wildfire debris flow susceptibility. One of my favorite things about it as an atmospheric scientist is that it considers heterogeneous precipitation in space and time, which I think is pretty important. And I think it performs admirably. It's missing a lot of components to be able to predict an actual debris flow, but it does identify areas that are susceptible to debris flows. And I mentioned way back at the beginning that I study lots of different things. And I should mention that this is the first time I've ever given an hour-long lecture on this particular subject. And I have like an entire hour more of slides I can show. I obviously did not plan well. So I think I will stop here and not take up too much of your time, and I'll take questions. Thank you.
Thanks so much, Dan. That was super interesting. I read your papers, but it's really cool to see it live. So we'll start with questions. Thorsten.
So I'm kind of stuck on your first slide in the sense that the degree to which we can use physics or chemistry-based models to predict anything, right? And so, for example, a while ago, we had a climate guy here who doubled resolution on these GCMs, and the results were not just, quantitatively, but qualitatively different, telling us we really have no idea how to parameterize eddy transport and stuff like that. Of course, you're looking more at sort of the weather side of things, where we know a little bit more. And my sort of worry, though, is how well do we know how to transition, right, between sort of looser physics to more well-constrained physics. And clearly that depends on not just the temporal, but also the spatial scales. And sort of bring it back to your last slide a little bit. What I wonder is what it means if a model performs admirably, right? So you showed us, for example, the porosity example, where instead of trying to optimize this other model, you throw more data at the problem, right? So you have resolved and improved measurements, for example, the porosity. And so you would expect that better measurements give you an improvement in the models, even sort of neglecting all the physics besides conservation of mass, right? So I wonder if you could comment on which parts here of the model should we believe in terms of the physical parameterizations, and what parts of the models are due to improvements in measurements, right? And then there's sort of two sides of the measurements. When you looked at the porosity stuff, you saw that in like close to Monterey, there was like offsets, right? Very different porosity values. And then things were finer scale. So you expect bulk different behavior and then differences in the time dependence because you just have more fine grained stuff.
Yeah, I think one of the things I'll mention as an atmospheric scientist talking about hydrology is that typically when you read these hydrology or geomorphology focused studies, their number one form of uncertainty is the precipitation. So even our ability to understand how much rainfall is falling out of the sky is highly uncertain. And I have a second project going that's somewhat similar, but more focused on constraining uncertainty and precipitation that's falling out of the sky associated with particular sort of extreme events in California. And what most folks use that work from that paradigm of intensity duration, they use a NOAA product called Atlas 14. Atlas 14 looks at precipitation observations through as long as we've had gauge observations of precipitation. And so all these intensity duration curves are based on just these gauges. But then NOAA somehow interpolates them to the entire CONUS, right? So it's a gridded product. But it's only one estimate of intensity duration. And all of the thresholds of debris flows and landslides are based on this one precipitation product, which is itself probably highly uncertain. And based on our comparison with other precipitation data sets, also definitely highly uncertain. And so I think that's important to consider. Like number one, even the precipitation is highly
observation side, right? And so clearly, if you have better observations, it's going to do better. But with your model, you can ask these questions, right? You can take the bad precipitation model and the good precipitation model, but then also change the physics. I mean, if you take the bad model and you improve the precipitation, does that explain most of the improvements, or do you actually have to add the fancy physics and parameterizations to get closer to the predictions?
I missed a couple of words in there, but I will attempt to answer your question. Yeah, so I mean, we could run sensitivity simulations with bad precipitation and good precipitation. In fact, even with this modeling setup, we've done other results where we use different precipitation data sets, but we don't necessarily know which one is right? And so with the model framework, the challenge is that our product, the thing that we're looking to simulate, we don't necessarily have great observations for even, right? So I'm just talking about uncertainty and precipitation, but we don't necessarily have the products that we see on the ground in terms of observations. And so if we're talking about debris flows, we can see that there's a thing sitting there on the ground. And so that's an observation, but our model doesn't even suggest that it's attempting to simulate putting things on the ground. It's doing something even different from that.
Okay. Nice stuff. Really cool. So here on the Gulf Coast, when a tropical storm hits, on social media, people start posting a lot about the stream gauge data to try to figure out where there's going to be inland flooding. And so how applicable would your kind of modeling scheme and updating the soil be to like urbanization and stream flow for predicting when a storm comes through? Because there's going to be a line where they actually show the stream gauge and then some prediction. And so do you think your model could be an improvement on that in terms of,
Yeah,
for the
not
people?
myself, but other people are applying this to urban settings.
Wow.
In fact, Argonne National Lab got funded to do an urban field lab campaign, which was like a $20 million project. And there are people within that collaboration that are attempting to take the WRF-Hydro model, but apply it to a place like Chicago. Chicago doesn't get the tropical storms that you're referencing, but we do get, we often get flooding because many parts of the city were built on low-lying areas, so on and so forth. And having a better understanding of soil properties and the impermeable surfaces is hyper important to being able to predict flooding in urban environments.
So do you think it would be operational, like be used operationally?
I think it could. Yeah, I don't think it's there yet, but I think it could be. I mean, what I've done, and from an operation, like I look at what the USGS has that's out there, and I fantasize about the idea that, okay, maybe 15 years in the future, a model like this could be used to inform from an operational perspective. Maybe we'd have that much confidence in it. But there's a number of things that I'm not that confident in at this stage.
So I actually had a question on something else, but I'll also respond to that because we have one of the IFLs for the Beaumont, Port Arthur area where there is a lot of tropical cyclone rainfall. And they're using these like local hydrologic models or like locally parameterized hydrologic models. And to get to Torsten's point as well, I think when you're getting to that local scale, having your local conditions be properly parameterized from observations ends up being more important than the physics of the model. Like the physics of the model is more or less right, no matter where you are, but if you don't know what's happening on the ground, then it doesn't do well. Okay, but my question was about this non-stationarity issue. So, you talked about how precipitation non-stationarity is obviously problematic, but then the pre-post wildfire is also an example of non-stationarity in the form of like non-stationarity in the land surface cover, right? So even the things that you're parameterizing the model with are not necessarily stationary. And I'm curious if you have a sense from like your work or other people's work, what form of non-stationarity is more important, maybe particularly for the case of debris flows in California? Like, do we have a sense of how much the changing precipitation statistics are going to drive changes in debris flow versus changes in land cover, changes even in like the subsurface hydrology over time?
Yeah, I think that's a fantastic question, and I don't have a good answer for you. I think that sort of investigation. I was just talking to someone about these slow-moving landslides, and the fact that the plumbing that is driving them. You might have an atmospheric river, and maybe the atmospheric river, or you might have a series of atmospheric rivers, but maybe the atmospheric river is influencing the groundwater in a way that it once wasn't, right? And so it's driving these changes in the slow-moving creep of the landslides. And I don't know whether that outweighs the non-stationarity in other ways or not, but I think those are fantastic research questions.
This is exactly connected. If you don't have the physical parameterizations right, then your derivatives with respect to the change in the conditions will not be correct, right? And so it matters if you have super good observations, right? And then say whatever, you just compute the catchment area and make sure that mass is conserved, and then you're fitting somehow, right? That's the way to get an operational model. And that's why my question was, how much better is it if I put in more complex parameterizations, and how can I validate those parameterizations that I have some confidence that if the conditions change, it still works, right? So it's this second order improvement in the physics of the parameterizations that would be meaningful, because otherwise I can just fit something and it's going to work as well as I have the data, right? So I think these things are linked.
Yeah, I would push back that I don't know that we have fantastic observations. We certainly don't in some pieces of this, but I do think, the beauty of working with numerical models is that we can go in and test the individual components of it, as long as we do have some observations for that. And so that is a way ahead.
I'm gonna have to cut it off there because I think some people have to go. Yeah. Budget Council has to go to your meeting. So if you're part of that, please go. Yeah, sorry. Thank you so much, Dan. Dan is here for the afternoon. Maybe he'll be at happy hour at ABW at 5. So yeah, please, yeah, join any of those things. And students and postdocs have an opportunity to have lunch with him like right after this. So awesome. Thank you. Good job. Right. You had how many more did you?